All right, we'll start. So you have seen the thumbnail already and the caption already. So you know what we are going to talk about today. Right, this is about DTL and TTL, right? And very emerging field, emerging side of electronics that popping up nowadays, right? So we'll see how it goes. And for this, the basic digital knowledge is required, right? So therefore, I will quickly recall what we need from digital first before we jump into DTL and TTL parts, right? So first we'll start with DTL, right? For that, these are the logics we need, right? So DTL means this, DTL. DTL means diode transistor logics, diode transistor logic, right? Diode transistor logic, that is called DTL, right? Now for this, from digital electronics, this is what we should know beforehand from digital, right? First thing is about the NOT gate. First thing is about the NOT gate. About the NOT gate, right? Say inputs of the NOT are A and B, right? Let me draw the circuit also. If I draw the circuit diagram, right? Circuit diagram of a NOT gate is this, no? Circuit diagram or the circuit symbol of a NOT gate is this, right? Say this is F, A, and output is F. Output is given by A bar. Then the truth table is like this, A, and F is actually A bar, then 0, 1, this becomes 1, 0, right? This is about a NOT gate, and then we need the OR gate, right? OR gate. About O, the circuit symbol is this, right? About O, the circuit symbol is this, say A and B, and the output of O is A plus B, right? Or we call A or B. And the truth table, there are 2 inputs and 1 output. Then A, B, F is A plus B, right? Then 0, 0, 1, 1, 0, 1, 0, 1, 0, 0 means 0, then 1, 1, 1, right? About the OR gate. And about the AND gate, circuit symbol is this, A, B, say output is F is A dot B, that is called A and B, right? And the truth table is like this, A, B, and F here is A dot B, F is A dot B. Then 0, 0, 1, 1, 0, 1, 0, 1, right? When both are 0, 0, when 1 is 0 or 1, still is 0, 0, 1, right? So this is the basic knowledge you required for the DTL part. First, before we start, right? This comes from digital, and for DTL, some more things are required. I will recall it when we are there, right? Now, DTL means something like this. Now, first idea is we know how to form a NOT gate using transistors, no? Right? That is what we discussed as functioning of a transistor as a switch, right? That's a separate theory part we discussed in the class, right? Functioning of a transistor, bipolar transistor as a switch, right? Now, to recall about the NOT gate, right? You have to know this. About the functioning of a transistor, bipolar transistor as a switch, right? This is actually going to be a NOT gate. Right? And this is how it's gonna function. See, look at here. If we are using a transistor as a NOT gate, right? Right? One thing is there's no resistor connected to the emitter, and is directly grounded. And 2 resistors should be chosen for RC and RB, right? 2 resistors should be chosen. This is actually VCC of this transistor. Say that is at +5, right? And this is V in. So what I was telling was, you have to select 2 resistors for RB and RC as the transistor is functioning only in the cutoff region and the saturated region, right? So if there's no current in the transistor, that is in the cutoff region, right? But when current flows, transistor should not be functioning in the active region. It should be directly jump into the saturated region. In such a way, these two resistors should be chosen. Otherwise, for each value, for any value of resistor, this is not going to function. Right? So this is RC and RB. For any value and each value of resistor, this is not going to function. That we have to choose. Right? Then, in this case, transistor only functions in either in cutoff region, or if current flows, that is in saturated region. Right? Then, see what happens. Now, if I consider two voltage values of V in, let's assume this as a silicon transistor, and this voltage barrier here is VB, and we know this voltage barrier of the transistor here VC, and V out is taken from this point, say that is F. V out is taken from here, say that is F, that is output. Right? Then, in terms of voltages, now if I check this, see what's going to happen. Right? See what's going to happen in terms of voltages. This is called voltage wise. Right? Voltage wise. Right? See, now for V in, we can have two values. Right? For V in, let's have 2 columns, that's enough. V in and directly F. Right? F is our V out. F is our V out. F for, say, that is VF. Okay. Then when V in is 0 and V in is 5 volts, right? 0 volts, 5 volts. I'm going to check on these values. See what's happening now. When V in is 0, we know for a silicon transistor, it needs minimum of 0.7 volts to make it forward bias. That is the voltage barrier of the transistor. Right? That's a voltage barrier of the transistor. Right? Without satisfying the voltage barrier, without exceeding the voltage barrier, no current will pass through. Then, when V in is 0, there's no potential difference of 0.7 volts across B junction. No? Because this is also at 0, this is also at 0. Right? Then, when there's no potential difference of 0.7 here, transistor functions in cutoff region. Right? When there's no potential difference, BE junction is not forward biased. Right? When V in is 0, logically, right, BE junction is not forward biased. Right? Since BE junction is not forward biased, right, transistor is in cutoff region. No current flows in the cutoff region. No current flows. If no current flows, we know there's no current through RC as well. If there's no current passes through RC, there's no potential drop or voltage drop across RC. Then if this point is at 5, F is also 5, then this is 5 volts. Right? And then when V in is 5 volts, see what happens. When V in is 5 volts, now it has satisfied the potential difference of 0.7. Now BE junction is going to forward bias. Now in this case, BE junction is forward biased. Then when it is forward biased, as I told you, right, this transistor directly jumps to saturated region. Right? Now it is in saturated region. Right? It is in saturated region. So we all know that in saturated region of a transistor, VCE equals 0. No? In the saturated region of a transistor, VC equals 0. Now VC is equivalent to my VF, because this is taken from the collector. This is collector base and emitter. Right? This is taken from the collector. Then VCE is VC minus VE. Now transistor is in saturated region, which means there are current flows. Right? All IC, IB and IE are there. All currents are there. Now when current flows, there's a potential drop across RC here. Right? Then that is not 5 volts now. Now we can check from this side. We know earth is E is grounded, no? Right? Or emitter is grounded, no? Since emitter is grounded, we know VE here is 0. Now what happens? Then it says VC equals 0. Now VC is my VF, no? Output is taken from VC. Then this becomes 0. Right? Which means functioning of a transistor as a switch is exactly equivalent to, see, this is a very familiar one, exactly equivalent to, therefore not gate. Now if I convert this to the digital or the binary, this voltage wise, no? We can write the same thing digital wise, right? Digital wise, if you write this, right? If you write this digital wise, see what comes. V in digital wise, V in and Vf, right? Then digitally, 0 is considered as 0 and volt 5 is considered as 1, no? Then 0, 1, this becomes 1, 0, right? So this is exactly a NOT gate. This is exactly a NOT gate. Then functioning of a transistor as a switch is equivalent to a NOT gate. Now, if we draw the NOT gate, right? If we draw the NOT gate, this is how the NOT gate here is, right? This is how the triangle of the NOT gate here is. This is how it is. See, this is how it is. That's why we have only one input for a NOT gate, right? We have only one input, right? That's a limitation we have in a NOT gate because of this, because we are using a transistor functioning as a switch, right? Then this is equivalent to a NOT gate, one logic of this transistor, right? Then I'm going to take this idea forward, right, to the other gates. I'm going to take this idea forward to the other gates, right, using diodes and transistors. Now, NOT gate is demonstrated. NOT gate is demonstrated using a transistor like this, right? That's the first idea. Then this is a NOT gate. Then without mentioning the gate, now I'm going to give you the circuit, right? Then let's see to which gate that is going to go into, right? Let's see to which gate that this circuit is going to take you to, right? See, now if I connect a circuit, like this, if I connect a circuit like this using two diodes, right? Now for our ease, let's say these diodes are D1 and D2 for these of reference, right? Right, like this, and say output is taken from here, and these two inputs are A and B, right? And consider both diodes as silicon. Consider both diodes as silicon. And this is a resistance AR. Right, now, if I check what's happening here voltage wise, right? If I check what's happening here voltage wise, see, voltage wise. Now, we have two inputs. Then A, B, F, no. Then let's say VA, VB, and VF. We have four possibilities like this: 0, 0, 1, 1, 0, 1, 0, 1. Right, voltage wise, sorry. Then 1 kilogram 5, 5 volts, 5 volts, then 5 volts, 5 volts. Right. See what happens now when both are 0. Now we know since there is a silicon diode, right? In order to forward bias the diode, still we need 0.7 volts, right? We need 0.7 volts across the diode to forward bias it, right? Now for the first scenario, 0, 0. See, A is at 0. This end is also grounded. There's no potential difference of 0.7 across these two. Then this diode is not forward biased. Right? If the diode is not forward biased, and check the other one also, 0, 0, D2 is also not forward biased. Right, now in this case, what has happened is, right, under this scenario, what has happened is D1 is not forward biased, right, and D2 is also not forward biased, right? If D1, D2 are not forward biased, no current flows in the circuit, no current flows in the circuit. If no current flows to the resistor as well, right? If there's no current flows to the resistor, there's no potential difference across the resistor, right? Now what happens if there's no potential difference across the resistor? If this point is grounded, F is also becomes the same point, it becomes 0, right? So simply when both are 0, Vf is 0. Right, now go to the second logic. Second logic means second instance. VB is 5 volts. If VB is 5, see, if VB is 5, this end is at 5, this is at 0, then 5 and 0, it has that enough potential difference to exceed 0.7, right? If there's 0.7, then the diode is going to function. But still, D1 is not functioning because D1 has no potential difference. Then D1 is not forward biased, but D2 is forward biased, right? When D2 is forward biased, we know it is going to keep the potential difference of 0.7 across this, no? A potential difference of 0.7 across this when it is forward biased, right? Then when VB is 5, if there's a potential difference of 0.7 across the diode, this point is 4.3 volts, right? This point is 4.3. 5 minus 0.7 because there's a 0.7 across the diode. This is 5, VB is at 5. Then F is 4.3 volts, right? Now, similarly, if you check this instance, now A is 5 volts, right? A is 5 volts, but B is 0. When A is 5, this is going to get that potential difference. Then D1 is forward biased. D1 is forward biased, but D2 is reverse biased, right? Then when D1 is forward biased, there's a potential difference of 0.7 across D1. Then from 5 to this point, 0.7 is less than this point, then 4.3 again, VF is 4.3. Alright? This point is 5. This point is 5. Then across this, it has a 0.7 when it is forward biased. Then 5 minus 0.7, 4.3, that is equivalent to 4.3. Right? Then VF is 4.3. Now, when both are 5 and 5, both D1 and D2 gets the enough potential difference, then both are forward biased. In that case, both are forward biased. When both are forward biased, both has the potential difference of 0.7 across each. Then 5 minus 0.7 is 4.3. Again, VF is going to be 4.3 volts. Right? So when we convert a voltage-wise table into a binary or the digital table, right? Lesser value is considered as 0, higher value is considered as 1. Simple as that. Right? Now, lesser value is 0, higher value is 1. Convert this table to the digital circuit or digital table, digital wise, what has happened? Let's say these inputs are A and B, right? Let's say these inputs are A and B, and the output is F, right? 4 possibilities, right? Then 0, 0, 1, 1, 0, 1, 0, 1. Lesser value is considered as 0, higher value is 1, 1, 1, 1. What is this? A familiar, a popular digital gate, logic gate, that is the OR gate. Then this is the DTL circuit of a OR gate, which means this is how the OR gate can be demonstrated using analog circuits, right? So usually for the demonstrations we use transistors and diodes, right? Then this is the analog circuit of an OR gate, right? Then when we draw the OR gate, this is how we draw it, right? Inputs are here at this side, and the output is here. See, මේක තමයි OR gate එක. Got it? So this is what we draw as the OR gate. Right? This is simply the inside the OR gate using analog. Right? Let's go to the next. Right? This is a simple thing. Right? But I thought of sharing because there are students who are kind of struggling when these kind of DDLs are given. Right? And DTL has already been come in the exam, right? And since DTL has already come, right, there's a high possibility of coming a TTL this year or maybe in the future, right? Now I'm targeting this year now, so there's a possibility of coming a DTL or TTL, but it can be kind of more towards TTLs this time. All right, then the next one. See, I'm going to do a small change for this circuit. I'm going to do a small change for the circuit. Right? I'm going to switch the side of the resistor like this. See, I'm going to switch the side of the resistor like this. Right? And the diodes. Now, let's say this circuit is right converted into something like this. This is grounded, right? And a resistor is here with this voltage 5 volts, right? And the output is now taken from this. Output is taken from here. Say these are D1 and D2 again for our east, right? They are D1 and D2, and inputs are A and B, right? A and B, and let's consider both as silicon diodes, right? Now, again, if we check the same voltage wise, if you check the same voltage wise, see, if you check the same voltage wise, VA, VB, and VF, voltages of these four, right? Then voltage wise, 0, 0, 5 volts, 5 volts. Then 0, 5 volts, 0, 5 volts. Right. See, now when VA is 0, when VA is 0, right, this side has 5 volts, VA is 0, then it has the enough potential difference across this. It has the enough potential difference of 0.7 across the diode to forward bias. One side is at 5, the other side is at 0. Similarly, across D2 also, one side is at 5, the other side is at 0. It has the enough potential difference across this, right? Enough potential difference across this. Then they are going to forward bias. Then under this condition, D1 is forward and D2 is also forward. When a silicon diode is forward biased, it keeps a potential difference of 0.7 across it. It keeps a potential difference of 0.7 across it. Now, VA is 0, that is at 0 voltage. Then this difference is 0.7 volts, right? Look at the word. This difference is 0.7 volts. When this is 0.7, this point should be 0.7 volts. No? 0.7 and the difference is 0.7, then only VA can be 0. Now, if you argue in the other way, VA is 0 now, and potential difference here is 0.7, then this point has to be 0 plus 0.7, 0.7. Right? Then VF becomes 0.7 volts. Right now, when VB is 5, for 0, I have already argued, no? When VB is 5, VB is here, 5 and 5 means no potential difference here across this part of the circuit. Then, in that case, D2 is not forward biased, but D1 is. D1 is still forward biased, but D2 is not forward biased. Since D1 is forward biased, there is a potential difference of 0.7 across D1. Again, VF becomes 0.7. Again, VF becomes 0.7. Right? And under this condition, right, there is no potential difference across D1 as this is 5 and 5. Then D1 is not forward biased, but there is enough potential difference across D2, 0 and 5. Then only D2 is forward biased. When D2 is forward biased, potential difference across D2 is 0.7. Then because of that 0 plus 0.7, this point is 0.7, which means VF is also same 0.7. Right? And finally, when both are 5 and 5, right? 5 and 5, no potential difference of 0.7 to forward bias it. And here also, 5 and 5, no potential difference to forward bias it, which means both diodes are now reverse biased. Both diodes are reverse biased. When both diodes are reverse biased, no currents are going to flow through the diode. When diodes are reverse biased, no currents are going to flow. Then no current flow here, which means no current flows here in the entire circuit. Right? No current flows in the entire circuit. If no current flows, there is no potential difference across this resistor. There is no potential difference across this resistor. Right? There is no potential difference across the resistor. Right? If there is no potential difference across the resistor, right, this 5 volts remains unchanged up until here because there is no potential difference across the resistor. If this is 5, this is also 5, then VF becomes 5. VF becomes 5. Right? Now, if I convert this voltage values to digital values, right, again, you are getting a familiar circuit, familiar truth table, right? You are getting a familiar truth table if this is converted into binaries again, right? A, B, and F, right? Then 0, 0, 1, 1, 0, 1, 0, 1. Then lower value is considered to be 0, and the higher value of the set is considered to be 1. 0, 0, 0, 1 means this is exactly the truth table of a AND gate. So this is an AND gate. This is the demonstration of an AND gate using diodes, right? Demonstration of an AND gate using diodes, right? Now, this is how we use the AND gate with 2 inputs, right? This is how you draw the AND gate. No? Output is here, inputs are here, right? Simply, this is the AND gate. This is the AND gate, right? So, from your side, this is what you should know, which means this is how you should know about this logic. Logic means you should be able to argue when this kind of a circuit is given, right? That is the expectation from your side. When it comes to questions, right, these circuits can be given, and sometimes a modified circuit to this can also be given. Then when that circuit is given, you should be able to argue and analyze the given situation, right? Now, this is the theory part here. This is only the theory part here, right? And sometimes when it comes to questions, you can be given a modified circuit as well, right? And in past papers, the exact these circuits has also been come, right? They are the exact standard circuits, right? But always there's an opportunity, there's a chance to modify this also, right? So when a modification is also given from your side, you should be able to argue like this, starting from the points, argue, right? So that is what you should know from your side. And this is not a big deal, a small thing, but since you should know about this, right? I thought of making some kind of awareness among you. That's why I'm recording this video, right? So I think it's clear enough. I think it's clear enough, right? So this is about DTL, diode transistor logics, right? Diode transistor logics. And the next thing I'm going to show you is TTL's transistor logics, right? Then let's see what's happening there.